The LOFAR Survey's Key Science project team is currently meeting in Leiden. This team has been working on a new set of surveys from the LOFAR radio telescope. LOFAR is a low-frequency radio telescope spread across Europe and now brings together more than 150 radio astronomers working on this new, exciting set of results. The results are now published in a special issue of A&A. And I know, and you will hear, many astronomers who are truly excited by the results coming from these new surveys.
In the evening when it's dark and we look up, we see stars. If you take a radio telescope and we look up, we see mainly emission from massive black holes. Those are giant objects that are located at the centers of galaxies. What we will study with LOFAR is the very first black holes. And we hope to then answer the question, where do they come from? And this is something that really fascinates me.
So at the heart of every massive galaxy there's a supermassive black hole. It can be more than 1 billion times the mass of our Sun. These black holes are pretty messy eaters. When gas falls onto them, they emit jets of material which we can see at radio wavelengths. LOFAR's got a remarkable sensitivity, and that's allowed us to see that these jets are present in every massive galaxy, which means that maybe sometimes more slowly or sometimes more quickly, but these black holes never stop eating.
I'm using the LOFAR survey data to understand some of the most energetic objects in the universe. It's believed that there's a supermassive black hole at the center of each galaxy, and some of these black holes, as they swallow up material, are emitting jets of plasma deep out into space. And I'm looking at these jets which are pointed directly at Earth in the LOFAR survey data, and comparing this emission with other emission at optical and X-ray wavelengths, with the point of trying to understand how these jets arise in the first place.
Galaxy clusters are the largest gravitationally bound structures in the universe, and the merging process between clusters of galaxies reveals the large-scale structure. When we look at galaxy clusters in optical observations, we just see the individual galaxies and a black space in between, which appears empty. But with radio observations, we can see large-scale diffuse sources filling the intercluster medium, radio halos at the center and radio relics on the outer edges. These sources are coming about from merging process of clusters, from turbulence and shocks. With LOFAR, we can detect more of these sources and understand what's powering them.
We know since 50 years that when two galaxy clusters merge, they can originate radio emission on the cluster scale. This is because particles can be accelerated by the merger process. What we have seen now with LOFAR is that even clusters that are not undergoing this major merger event do show in some cases this emission on the cluster scale. This emission is very, very weak, so it's very hard to detect, and only LOFAR is able to detect it so far. And it is very important because it's telling us that there are other mechanisms that we didn't know before, in which the particle acceleration can be triggered, even if clusters are not merging.
In case of nearby galaxies, observing with LOFAR means opening a brand new observational window. It turns out that the electrons that stay behind the radio emission travel further away from the galactic disks, making them appear larger. And so it happens for galaxy pairs or galaxy groups. They are all accompanied by large radio halos, something that you can see only with LOFAR.
LOFAR is recording radio waves emitted billions of years ago when the Sun and the Earth did not even exist yet. But LOFAR is producing insane amounts of data, and we have to process the equivalent of 10 million DVDs. And to do this, we have to invert a gigantic system of equations. And this was made recently possible by some mathematical breakthrough, or the way we understand interferometry. And this was implemented into software, making LOFAR surveys possible.
So we go forward from here. We have covered about 1/4 of the northern sky. And over the next few years, we will be continuing to cover that entire sky and the entire radio universe. So just imagine some of the discoveries we may make along the way, and I certainly look forward to it.